So we shall study today about the various processes in computer programming, because finite element method is a computer based method where the data of the structures are given as input data. In the pre-processing, all the material data and the structural breakup data, these are provided in pre-processing, and then all these data are processed for a particular structure where these in the processing the unknown displacements are found at various nodes. Then after that, the post-processing, in the post-processing we can calculate from the displacements the stresses and strain and other various parameters in the structures for the analysis. Here is the algorithm of the computer program. First is pre-processor, as we have discussed, that is input data. It includes control data, material data, nodes, various nodes and element definitions, boundary conditions and other loads which is applied in the structures, which is created. An element file and load files are created. Then the element is formed, that is the element stiffness matrix is formed, and the stiffness matrix is stored in the element file. Then the system stiffness matrix is formed by taking the input data, that is assembly data, assembling of the elements into a global stiffness matrix, or it is called also system stiffness matrix. Then these boundary conditions are applied on these stiffness equations in the matrix form, and then displacements are calculated, which is called actually processing. System stiffness matrix, element stiffness matrix, these are coming under processing after the finding out of the computer displacements, where the equations are solved as kd equal to f. K is the stiffness matrix, d is displacement vector, and f is the force vector, which is displacement is the unknown, which is calculated as inverse of k into force matrix. And in this calculation, load file is taken as input. Then come the processing, that is the stresses are calculated. Stresses are calculated from the displacement vector d, and applying various relations we can find out the stresses and strain, and these files are stored as displacement stress files. Then in the post-processors, these final results are shown in form of graphs or in form of the colored figures of the structures, where the colors indicates various level of stresses and strains. Here the pre-processing, as we have discussed, a model is created which includes nodal point locations, element selections, what type of elements will be taken. There are various kinds of elements, nodal connectivities, how the nodes of the elements are connected to other nodes of the element, other element nodes. Then material properties of elements are input, are given as input, then displacement boundary conditions are given as input, and loads and load cases also are given as input. Then preprocessor assembles data into format for executions. Then comes the processor stage, where these codes which solves the system equations, that is, generates the element stiffness matrices. Then these element stiffness matrices are stored in files, and these element stiffness matrices are used to form a global stiffness matrix or structure stiffness matrix, which is assembled. Next, the displacement boundary conditions are applied to prevent rigid body motion. Otherwise, you cannot get the solution, proper solution. That is, the singularity will arise. Then solution gives the nodal displacements in the processor, and with the element informations, the strains and stresses are calculated. Comes the post-processing cases, where output data is difficult to use as a numeric form. Hence, to graphic displays, contour plots and graphs are created in this post-processing, which magnifies the nodal displacement. Nodal displacements are single-valued. Stress at a node can be multi-valued if multiple elements are attached to the node. Stress is found from within each element. That is, you can find out the stresses in different element may be different. That is, in different directions, the stresses may be different. Then comes the post-processing stage again. The deformed displacement and consistency is checked. Then stress and is compared to the approximate solutions. Then redesign. If these first analysis results are not up to standard or inconsistency is there, then we can refine the model. High stress and rapid variations reduce element size. Low stress increase element size. Analysis is again carried out and checked for converging conditions. Here in the form is the various colored forms showing the different stress levels or the strain levels